Hello, welcome back to Petrophysics Rocks. This presentation is saturation height shootout. This is where I take a whole bunch of saturation height functions and compare them, and can I come up with which one's best? Spoiler alert, no, but it's still worth watching, hopefully, throughout, and you'll find it useful. For those of a non-petrophysical persuasion, saturation height functions are the equations that we use to distribute hydrocarbon volumes in our reservoir models in the subsurface sort of stuff. So they're the equations that describe how oil fills the pore space. And it's a bit of a hot topic at the moment in petrophysical circles, in petrophysical pubs up and down the land. Which one is best and which one is most appropriate? Well, here I'm comparing 7 or 8 of them, and hopefully you'll find this useful for those who are more petrophysical persuasion. Otherwise, hopefully the rest of you might just be able to stick in there for some of the Excel animations and stuff like that, and maybe give you some ideas about how to do some data analytics in whatever sphere of work that you pursue. Please do give me a like and subscribe. We're close to 500 subscribers now, so we're getting up there, and I appreciate everybody's contributions down below in the comments. If you can make a comment down below and interact, that would be good. This one I'm hoping might raise a few eyebrows. There's still my link to the Archie Children's Hospital, the Aberdeen Children's Hospital there. I should give that a plug every now and again. There's a link down there. If you find any of this stuff useful, if you could just go and make a contribution, £5 or £10 or rupees or whatever, it doesn't matter, really matter, whatever it is, I'm sure they'd appreciate it. So without further ado, as I say, if you could give me a like and subscribe, that would be really appreciated. Without further ado, let's get on with saturation height shootout. Sorry, I did that the wrong way around, didn't I? Shootout. There you go. Cheers. Hello there. Welcome back. Welcome to saturation height shootout. Saturation height functions are the subject of many a heated conversation in petrophysical pubs up and down the land, and so I thought I'd add my 2 penneth to it by showing you a comparison of saturation height functions. Now these are what are used in 3D modeling software to calculate the amount of hydrocarbons in place in our oil and gas reservoirs. So they're quite important, and they form the link between geology and the static model of all the rocks and the dynamic reservoir modeling of how fluid flows through those rocks. So this is kind of like the link between the two, and this is really at the heart of what petrophysics is. So I'm going to show you a series of saturation height functions that I routinely use, and we're going to compare the 2, or compare the 7 I should say. You may be disappointed at the end. I may not come to a definitive conclusion as to which one is best. Everybody has their own favourites and champions, but this approach might help you learn to compare more than just the one. If I give you a saturation height function and you're the departmental manager, you're not going to know whether it's the right saturation height function or the wrong one. But by showing you 7 or 8 of them, then you can take a view too as to how valid you think they are. Okay, so without further ado, here is what I'm going to take. So I'm going to tell you where we are. I'm going to give you an example that we're working on. We're going to talk about my old saturation height modeling spreadsheet. We're going to discuss the Monte-Carlo stuff in a reasonable bit of detail, much to Mike Cooper's chagrin probably. And we're going to talk about some of my favorite functions, and then hopefully going to wrap up with some conclusions. I don't know whether I need to do the old paint a bit of background about myself for you, just quickly, in case this video goes viral and it's the first time you've seen me. My name's Graham Davis, and these are some of the companies that I've worked for in the past and some of the organizations that I've worked with. So I've been around a little bit, both big oil companies and small oil companies, and latterly I've been reviewing petrophysical models and auditing them and working out why they don't quite deliver what reservoir engineers promise oftentimes, and we're all to blame for the reasons why. So what I'm going to do now is I'm just going to go back to the North Sea. I know this channel seems to be a little bit North Sea biased, but you'll forgive me because that's mostly where I've got the data from. And we're going to go back to the UK, and then we're going to go this time around to the southern North Sea as an example. Before, the last few videos I've made have been up here in the northern North Sea, but this one's down in the south North Sea where all the gas fields are. And these reservoirs are quite interesting to work with petrophysically. So here are all the UK gas fields. Obviously, miraculously, there are no gas fields on the other side of the international line here because it's a UK invention. Okay, so here we are, offshore southern North Sea. So here's Norfolk down here, and Hull and Humberside are all up there somewhere. So we're going to take an example reservoir, and I've just happened to choose here is Ravenspurn. It's one of the first fields that I worked on when I started in the industry in 1985, 1986, and got involved in equity work with Hamilton Brothers and Amoco and BP, who were on the other side of the equity line. So we had some fun and games. Mr. Steve Cuddy, arguing with him back in the day. But nowadays, the field Ravenspurn is run by a company called Perenco, French company, and as interestingly enough, I point out here, this is a drilling rig. This big drilling derrick. Here's how we drill holes in it, and this thing here is actually the Ravenspurn platform, and it's not way off in the distance. It's actually that sort of size difference. Puts it into a bit of perspective when you consider that we're drill new wells through the platform here, and this is what's left to process the gas. This is the main offshore processing installation for the gas, and this is just a drilling rig that comes along and drills wells through it now and again. Anyway, all of that stuff which I'm not really qualified to talk about, so the surface stuff. We're interested once again in the subsurface. So here's an example well, and this well was drilled in 1986, which is just roughly when I was kind of starting. These wells are being drilled up, and so here is the raw log display, and this is an example of a Permian Rotliegend. Red Rotliegend means the red rocks, and here is a nice interval. Remember what I said in Petrophysics for Dummies? We shade the logs in yellow in sand, so the geologists colored this interval here, and you can see that these are terrestrial desert sands, wind-blown sands, and sometimes there are some fluvial, i.e. river dominated or wet interdune areas where the water comes in certain parts of the basin and deposits a slightly different type of sand. And I'll show you here that this big stuff here with a big yellow separation is Aeolian rock, and some of this poorer quality stuff is the more fluvially dominated rock. And here's a gas water contact, low resistivity. Remember from Petrophysics for Dummies, this is good rock quality. Here's some core data overlays in the middle of the gas affected logs. This is the sonic log, gamma ray. The resistivity increases, bit of invasion here, bit separation. Go back to Petrophysics for Dummies and you'll see. Here's some core data, core permeability up to this is up to 0.1 to 1,000. So this is 1 Darcy permeability. So this is good rock, and you can see that up here in the fluvial stuff, the wet rocks, the permeability is a little bit lower. Just file that away in your memory banks, and we might come back to that later in a later rabbit hole. And then below this we have the Carboniferous, which is deposited much earlier actually, and then there was an unconformity, i.e. a gap in sedimentation between these older Carboniferous rocks, which are fluvial, river-dominated sands and shales with swampy forests on the top, and this often leads to coals. Here you can see some some coals, which is where the hole washes out a little bit, and they have really low density. And they, if you're not careful, you can calculate 40 or 50% porosity in them, which, if you know anything about close hexagonal space packing, is not really a valid porosity. So these are coals, and that's typical of the swampy carboniferous environment. So anyway, that's a Ravenspurn example, just to show you the types of rocks that we're dealing with. These are not rocks laid down under the sea. These are rocks laid down in a sort of a desert environment. And if you refer back to my saturation height modeling, a practical approach, which I kicked out in 2011, that's a spreadsheet there, that a basic spreadsheet that I can share with you. If you email me, I'll share you the initial starting of this spreadsheet. But these days, 23 years later, 13 years later, my spreadsheets have got a little bit more complicated, and one of the things that I do in these spreadsheets is automatically kick out these reports. So for every saturation height function that I've put into the sheet now, I basically got a tab which reports the averages at the end of it, makes it all a bit more automated. I just worry about the regression fitting, and then the spreadsheet reports the analysis results at the end. So here is a saturation porosity relationship, which is kind of like a Buckles relationship. The original Buckles plots are sort of log linear or log plots or whatever, which were done back in the day to ease the computation and line fitting. By plotting it on log scales, it becomes a straight line. But I like looking at it on a linear scale, in a curvy linear sort of a way. And so this is my plot. So with increasing porosity, you get better gas saturation in this case, or oil saturation. And this is a typical relationship that we see within our reservoirs. But also on this report spreadsheet, what I normally do is I show the fitting parameters here. So this is the hydrocarbon volume from the logs, from the wireline logs that we measure, versus the hydrocarbon volume calculated from this function here. So you can see this is the goodness of fit. It's not bad. It's pretty good. We've got our usual regression statistics here, correlation coefficients of 97% sort of stuff in terms of oil volume. And still not too bad even on saturation terms. I often fit to hydrocarbon pore volume. I minimize the errors in hydrocarbon pore volume because that's what I'm interested in. I don't tend to fit on errors minimize the errors in saturation terms, because obviously we have quite high saturations in small porosity rock, and I'm not that fussed about those. The main thing is the big pore space, the big oil volumes, that's what I want to, or gas volumes, that's what I want to fit on. And also at the bottom of these plots here, you'll see that for each of the porosity bins, so from 4 to 8 PU, 8 to 12 PU, up to 20 to 24, 24 to 28 PU porosity bins, here are the average porosities, the average permeabilities by porosity bin, and also the average log saturation here by porosity bin. And then what I do is I report the average function saturation by porosity bin as well. So when you're looking at how well does your function fit, it's quite handy to look at, does it fit everywhere? Because overall you might get an average number. Remember, the average number is just one number, but it's often quite informative to look at the saturation match across a range of porosity bins and see how well you're doing. So here at low porosity ends, it's the average of 45% hydrocarbon saturation, and I'm calculating 48% here on my function. And at the high end, it's an average of 87% hydrocarbon saturation, and I'm calculating 89% with my function. So it's just handy to be able to check to see how your function is behaving over the porosity range. So this is the saturation porosity one, and here we have a height only one. So this is a height function. You can see obviously it tends to overestimate in the good stuff. underestimate in the good stuff and overestimate in the poor stuff. But overall, you can see that the correlation is not too bad. But this is just a single height function to fit there. Here's a lambda function. And if what would be useful if this is a lambda function, so this is the same data fitting the lambda function, which has got porosity terms in it here. So you've got low porosity, which is the average porosity is 6.8 pu, 10.4 pu, which is the average of the porosity bins. And you can see the idea is that the magenta lines are supposed to be in the middle of the magenta points, and similarly with the blue. So eyeballing it, it looks noisy, as petrophysical things often do, but you can see the match there. And if I toggle between functions, you can see that there's some sort of difference in behavior and fit. Here's the lambda function, the Thomeer function, which I quite like because it has a sort of a lazier transition zone here and a sharper one here in the good rock, which is kind of intuitively what you expect. Here's Steve Cuddy's foil function, his beloved foil function here. Everything's pretty constant above the free water level. And again, you can see that on average, the magenta points are going through here, and the fit is not bad here at all either. Perhaps undercooling this little bit here, more of which later. So that's the Cuddy function, a Skelt-Harrison function, well, a Skelt-Harrison asterisk function. The Skelt-Harrison function normally has just a height term in it based on typical core capillary pressure behavior. And what I've done here is I've modified the Skelt-Harrison function. I've put in a porosity term, a quality term. Basically, I've used this relationship here, which controls porosity and saturation, and I've used that as my A term in the Skelt-Harrison function. So it's got a rock quality term in it. If we can have a discussion about that later on if you like, but this is not necessarily a deep dive into these saturation functions, but it's more of, as I say, a comparison of them. So that's the Skelt-Harrison function. Again, they all do pretty good matches. Here's a Roger Jenner function that I came across in a report years ago. I haven't been able to find out much about it. It was in a Energy SciTech report. So for reasons which I won't go into here, I often just sort of carry that in my spreadsheet and compare it to, so you can see how these functions vary. I don't know much about Roger Jenner's SciTech function. If Roger emails me and explains it to me, that would be quite useful. And then here we have a Leverett J function, which has a permeability term in it as well. So there are proponents of Leverett J out there. Dan O'Meara comes to mind or whatever. But I do it as well. If I have to go down the permeability route, I will do. But if I always try and get the porosity ones to work first or whatever. And you can see actually I'm struggling a little bit here with this very sharp transition zone here with the J function. Again, more of which later. So it's not quite as good a match as other ones, but if you want to pause the video and capture any one of those, it's quite useful just to sort of see how I've got a range of saturation height functions and they all match differently. So the other spreadsheet that I have, or the other tab I have in my spreadsheet, is what I've called the TVD Slab HCIIP calculator. It used to be my STOIIP checker, but these days I just call it the FILLULATor, because basically what I have here is a series of horizontal slabs of rock that I've got from the geologist, the GRV, for each 50-foot slab or 25-foot slab here, and then I fill it full of petrophysical properties, average properties from my logs by depth slab. And you can see here that if I take the average net to gross, porosity, permeability, volume of hydrocarbon from my log saturation, a formation volume factor, and I multiply it all through, and then I can calculate a slab STOIIP. slab GIIP in this case, a gas in place. Now I'm going to show you this spreadsheet in a little bit more detail when I come to discuss the Monte Carlo aspects of this. But so for now, this is just petrophysical slabs times petrophysical properties gives you a GIIP. And one of the things that you can do is plot these up. So this is just assuming a fixed log saturation. So here is my GRV depth relationship. So this is the volume of rock above my contact. Here is the log average porosity. And in this case, it's 15.5 pu, which is the average of all of this stuff. It's weighted by GRV slab. So that's the weighted average porosity. The average water saturation or hydrocarbon is 22%. So that's 78% hydrocarbon saturation. And this is the volume of hydrocarbon calculated, this porosity times this this volume of water, volume of hydrocarbon saturation will give you this volume. And you calculate a J as well, which we'll see more of later. And this is the pore return plot. So this is the average porosity, 15 pu, and just under 100 millidarcies permeability. And that calculates out to give you 709 BCF, so 0.7 of a TCF. Now we can, instead of using a fixed porosity, we could take the porosity distribution in 10 percentile. So each one of these lines represent the 10th percentile of the porosity population. And you can see they're kind of clustered here around the mean, as you might expect. But 10% of the rock is out here at high porosity, 23% porosity, and there's 10% of it down at 7 pu. So this is the porosity range, and if we take that porosity range into our model instead, I'm still keeping the fixed porosity. That calculates out at 680 BCF. So we've gone from 709 to 680. So fixed porosity, fixed saturation for each of these porosity classes, which we know isn't that realistic. But anyway, so this is a fixed porosity, and we can put a height term in here, which is based on this function here. So you can see that put a little bit more hydrocarbon in it. So we're back up to 693 BCF now, just with this single height function. But again, it's a single saturation based on this height function. So if we want to put the Buckles plot in, the porosity relationship, you can see now we've got a variation in saturation with different porosities. So each one of these porosity classes picks up a different saturation here. And because we've got different porosities, by the way, this is the different permeability relationship for different porosities. And we're calculating some J's over here for the fixed different porosities. But still, that's a fixed porosity term. But we know that from our log data that we put into this, we've got this porosity depth relationship. Now, clearly, those of you who've seen my last presentation might be a bit skeptical about this line through this scatter of points. Oh, that's just a petrophysicist line. Well, go back to my trendy petrophysics presentation, and you'll see that this line is a real feature of the data. It's a mathematical fit to this data, so therefore we know that there's a depth trend. Again, I apologize. This is perhaps a more usual way of plotting porosity, increasing and our axes increasing this way. With depth, we decrease porosity, but it's sort of a convention in log analysis world that we have porosity increasing to the left and saturation increasing to the right, basically where we scale our logs. So if I just flip that around and plot a depth relationship here in our porosity, add this in just to confirm this is the appropriate depth a trend to use for this bin, you'll see that actually we've got now a change in our saturation profile. And if I just toggle back between the two, which takes a little bit of time, you'll see, you remember this is fixed porosity, so we've got a fixed saturation, and all I'm doing is I'm just putting in this porosity depth term, And you'll see now that the saturation changes. And this is, I just mentioned this because oftentimes we've not got a height term in here, but saturation is changing with height, and it looks like an apparent transition zone. And as Steve Cuddy likes to point out, what our resistivity logs are measuring is the bulk volume of water. And because the porosity is reducing with depth, then obviously there's less water, less conductive water in the way. So if we were measuring these in logs, we get this sort of apparent increase in water saturation, and it sometimes can look like what's called a pseudo transition zone. This isn't really a transition zone because, as you see, the saturation per porosity class is actually constant. But overall, the resistivity-based logs might give us what looks like a transition zone. So sometimes when you see log saturations and log fits to saturation, you kind of go, oh, okay, that's a transition zone. It's not. It's not a true transition zone. It's just an apparent transition zone caused by the decrease in bulk volume of water. Hopefully, that's not too unclear. So now we're down at 595 BCF. With the porosity depth trend. If I go back to this one here, so we've lost 100 BCF by using a depth trend, and a depth trend that obviously a lot of people won't necessarily like, but unless they go through and do the work, then you'll realize that it's real. So this is just a depth trend using just a fixed saturation porosity relationship. But again, and because we've got much more of a range in porosities overall, now you'll see that you're fully defining this pore-perm relationship. Okay, so there we've got the lambda function. Again, the difference between a lambda function and the Buckles function is not that dramatic actually. Down at 582 BCF, so dropped another 10 BCF. The lambda, Thomeer, 583, quite similar. All these are regression fits to the data. FOIL function, Steve Cuddy's FOIL function, again, you'll see down at it's the same in this particular case as my Thomeer function, and there's the Skelt-Harrison function, which again uses my original Buckles relationship, 588 BCF, so pretty consistent. Roger Jenner's function here, which I've already mentioned, the J function, 564, so that's a bit lower. You see it's not quite as sharp down here. So what I can do then is add a little bit of noise to the data. So this is my FILLULATOR in action. So the noise is based on confidence in the mean averaging and a quantitative petrophysical log analysis error. So I know normally that log porosity can vary in a single well by 1 plus or minus 1 PU if you've got core. If you've just based on log data alone, it's maybe up to 2 PU, plus or minus 1 or 2 PU. If you've got the sonic data, maybe plus or minus 3 PU. Those are typical errors in single well analyses, and maybe 5 or 6 saturation units. And this kind of translates in a single well to plus or minus 8 to 15% hydrocarbon pore volume. Now, if you've got more than one well, and then if you have the law of large numbers working in your favor, then some of those errors will cancel out. If you've got some well that's got a log calibrated high or log calibrated low, then randomly they might cancel each other out with the law of large numbers. But there will be some systematic errors remaining. If you've chosen the wrong water salinity in your calculations, then it will always be wrong, and they'll be systematically wrong in one direction. And similarly, if you know that your Archie parameters are wrong, then they will always be wrong. But some of them, like the net to gross and things like that, as you sample more and more of the geology, you'll reduce those errors and they'll regress to the mean. So a mixture of systematic errors and random stochastic errors may reduce the noise a little bit, and that's probably the subject of another video. In fact, if you go and check my residual oil video out, there's a discussion there. There's a discussion there about error analysis. So there's the petrophysical error in calculating water saturation, and then there's the geological error of not sampling enough wells, which I've kind of discussed a little bit in my trendy petrophysics and my sums and averages videos as well. I'll probably put some links at the end to those videos for further reading. But this error is my best guess at what the average porosity, water saturation, and net to gross variance is in this particular field. We can just you'll see that a little bit more in the Monte-Carlo discussion. But here's one sort of noise. If I F9 it and recalculate it, then I have a series of saturations and porosities that vary with time. And each time around, you can see that the saturation or the volume calculation varies a little bit. And so now you can see I'm halfway towards a Monte Carlo setup, basically. So here is noise. And so for each one of these realizations, I've got a variance in GIIP calculations. So that leads nicely on to, well, once I've got this set up, then why don't I go to do a full-blown Monte Carlo? And here you can see this is the range of this is the Monte Carlo that I ran, and with all the saturation height functions together. So by varying the saturation height functions in my Monte Carlo, I came up with plus or minus 3.2% hydrocarbon in place. So there's 3% error or difference by using different hydrocarbon saturation height functions, and this is the P90 and the P10 range of the GIIP as a whole. Now that this range is not just the range of hydrocarbon saturation height functions. This is the total range with all of the different parameters. But I am selecting all the saturation height functions, which were about 9 of them, if you like, and then they come in and calculate this saturation. So why don't we go and have a look at saturation height and how I set up that Monte Carlo approach. Hello there, welcome to the belly of the beast. Mike Cooper really likes it when I delve deeply into my Excel spreadsheets. Nevertheless, I think it's worthwhile just to show you how to lay things out and set things up for your own work. It may give you a few tips and pointers and some ideas how to proceed, but particularly I want to show you now the Monte Carlo version of my Slab STOIIP checker. This is my master spreadsheet with all my saturation height function work in it. It's a really complicated beast these days, so I don't give it out. It's not really fit for human consumption outside of my own heat-oppressed brain. So this is a spreadsheet within it that I've used to sort of verify saturation height functions and the impact that they have on STOIIP calculations, or hydrocarbons in place calculations. I asked the geologist for a GRV versus depth, a gross rock volume slabs by 50-foot slabs in this case. Actually it's 25-foot slabs in this case. So between these depths, this is the gross rock volume in cubic meters. So this is how much rock we have in our reservoir. And then I fill it, if you like, my FILLULATor, as I'm coining it now, with petrophysical properties and a selection of saturation height functions. Because this is my master spreadsheet, I've got all the saturation height functions available to me here. So I just can select a variety of saturation height functions and check the impact that using different saturation height functions has on the volume calculations. As you can see here, here's the GRV versus depth curve, and so there's a lot more gross rock volume lower down in our hydrocarbon column, and so therefore functions that are particularly affected by transition zones, where the saturation is not at full saturation, will be very sensitive. Some reservoirs obviously have very small transition zones, and it doesn't really matter what you do. the average saturation will be there or thereabouts, be okay. But in situations where the transition zone is a significant part of the GRV, different functions will behave differently. I got caught out in the early noughties. Somebody asked me if I could have one function or another, if they could use either one, and I checked it out, and the difference in my world, in just log analysis world, over my log population was just under 10% by oil volume. I said, yeah, sure, use either one of those functions, it's the same thing. But I didn't realize that in 3D, in the Petroleum model, when one of those functions was implemented, it increased the STOIIP by 34%. And that's when I started to realize, okay, the effect of this transition zone is important. So what I do nowadays is I get the GRV from the geologist, and therefore I weight everything by this amount of rock here, because although your eye is drawn to, and most reservoir engineers will tend to sort of use a fixed saturation, irreducible water saturation, and say, right, okay, that's what my reservoir is. Sometimes the effect of this transition zone can be quite impactful. So what I'd like to do here is show you how to do a Monte Carlo work, and we'll vary the saturation height functions and see what different saturation height functions, how that impacts the STOIIP or GIIP calculation, the gas initially in place. So this spreadsheet you'll see is, as I say, my GRV slabs times the log properties calculates out to be a GIIP by slab. And so this spreadsheet is laid out such that I've got these slabs over here, and if I move to the right a little bit, you'll see this is my porosity array, which I've already explained has 10% of each, the percentiles of each porosity population. So each one of these represents 10% of our porosity population. And then we have the selected saturation height function. So depending on which equation I choose, it selects a different hydrocarbon saturation to put in here and calculates out obviously the volume of hydrocarbon saturation. And here's the permeability array, air permeability and in situ liquid permeability array. And then I have the J function calculations, the various capillary pressure terms and J fitting parameters, and the average J saturation height function. Then I have a series of saturation height functions that I calculate the parameters for elsewhere in the spreadsheet, and I pick them up here, and I calculate a hydrocarbon array, if you like, for each of the functions over here. And then depending on which one I choose here, that depends on the function that is selected for the hydrocarbon calculation. So here it's using 4, which is the Thomeer function. If I select 3, it's the Lambda function. If I select 5, it's Steve Cuddy's foil function. If I select 6, it's the Leverett J function with the permeability term in it as well. So if I start out here with 4, which is a Lambda function because it looks quite pretty, and this is the inputs. Let me just go to 26 here. Right, so this is the function. Let me just add a little bit of noise in, and this noise is defined elsewhere in the spreadsheet. I've got these normal distributions of noise, which adds in a little bit of noise, and every time I press, it'll recalculate the saturation. Now I think because I'm running the video here, if I press F9, it's not refreshing as quickly as I'd like. Okay, well, I'll tell you what we'll do then. We won't worry about the F9 thing. There we go. I've got too much going on with the video recording, I think. But here is one of the things that I noticed the last time I ran my Monte Carlo work was I got this saturation distribution here. I noticed, and I'm thinking, oh, look at that, it's bimodal. I've got a bunch of saturation here at 80% oil saturation, gas saturation, and a series of them here. It's kind of what's going on there. And I think what's happening is that because in my saturation height function, I've got two options here: 0, which is use the zonal average saturation over the whole zone. Now, obviously, here I'm saying the zonal average is 22% of water saturation. So that's what's that? 78%. 78% hydrocarbon saturation. I'm going to use that as a fixed saturation. Now, particularly if I use a fixed porosity. Remember, we went through this last time. If I just got one porosity, the average porosity, which is whatever it is, 14 point something or other, nearly 15 pu, and the fixed saturation. So these are oil sum averages. We get 728 million cubic feet. Let me just actually take the noise out again. Hang on a second. Yeah, 700 billion cubic feet of gas. So 0.7 of a TCF. That's what you use if you get those single numbers. But let's not use a fixed porosity. Let's use the 10 porosity, and we'll use the porosity depth trend. And now we get 613. But that's still using a fixed saturation. And similarly, if I use the height only function, so that doesn't have a rock quality term in it as well, that actually has a little bit more hydrocarbon in it, 0. And these are kind of, so these are the 70 to 80%. So they don't take into account rock quality, they're just fixed saturation. And the reason that I included them was because oftentimes reservoir engineers kind of go, okay, let's just fix an irreducible water saturation for now for our reservoir, and the one that's most interesting to them is the irreducible in the best quality rock. This stuff produces dry oil or dry gas on test, and so therefore it's Darcy rock, so let's use 80% oil saturation throughout. And here you'll see that you significantly overestimate hydrocarbons by doing that. But I put it into the mix anyway because it's quite often done. But I don't think it's particularly realistic. So I'm going to add a bit of noise here. Obviously noise to the porosity, but in this case I'm still fixing the log saturation. But if I go to my Thomeer function, which has the saturation and porosity term in it, and what I want to do in my Monte-Carlo work, there we go. Let me just take that noise out again, just to show you. So this is without the noise, but with the depth porosity relationships in it. Add a little bit of noise, and therefore this is the first baseline simulation, if you like. But in my choice of saturation height functions, I only want to do, so here is the crystal ball add-in. As I say, this is what I use to do my Monte-Carlo work. Crystal ball is not cheap software. It's around about £1,000, so it's not something you use lightly. But if you have access to it, it's really useful. And I tend to prefer it over the Palisade at-risk software because you can take an existing spreadsheet and just add these forecasts on over the top here. So if I go into this one here, this is the net to gross of this particular layer, and if I define the forecast define the assumption, it's taking this net to gross here, and it's picking up the standard deviation from a table that I've got elsewhere in the spreadsheet. So you define your assumptions, and then you define these cells here as forecasts, which are the blue cells, the cyan cells. So I want to predict the weighted average net to gross, and I want to forecast the hydrocarbon saturation, the STOIIP or the GIIP in the end. So the green cells are the added ones, the crystal ball assumptions, and the cyan cells are the forecasts. Now, when I first put the spreadsheet together, all of these input variables were fixed numbers, and I put variance in them, and I used to crystal ball them all. So these would have all been green cells. But because I'm calculating a porosity by depth, and then I'm selecting a saturation height function, I need to update the saturation depending on which equation I select here. Crystal Ball doesn't allow you to use complex cells or cells with equations in as assumptions. So I've just got these fixed GRV and net to gross ones as assumptions in Crystal Ball, and I rely on generating the noise, if you like, the variance from normal distributions that I've put in elsewhere. Now you can go back to my conglomerator spreadsheet, the problem with rocks presentation, and my Drillulator one, and I've shown you how I calculate using random numbers and a lookup in the statistical noise and add that in. So the noise is coming from the spreadsheet, and the green cells, the noise is defined in Crystal Ball. I hope that's understandable. But as I say, one of the things I noticed, the last one I did, is I've got this sort of bimodal saturation distribution. And I think that's because I'm using the first two, the fixed saturation and the height only saturation in my spreadsheet. So if I want to just change that, I'm using equation 0 and equation 1, fixed height only. So this doesn't have any rock quality term in it. So what I'm going to do is I'm going to run a simulation now with a minimum of 2. So it's just going to choose these last 7 saturation height functions. It's just going to select from those, and then I'm going to run the saturation. I'm going to run the FILLULATor and predict what the saturation, what the GIIP is going to be. So if I press start on that there, then hopefully the charts will appear. So here we are, trials number 16, and here it runs through, and you can see if I show that it's selecting here. If I see this H2, 8, 7, it randomly selects or uniformly selects the different saturation height functions and applies it to these GRV slabs, and then the forecast is up and running. So I'm just going to let this rock out for a little while, and I'll come back at the end when we'll see what the results are, and I'll show you how to extract the data. Okay. Okay, just coming up to the end now, the last few simulations. There we go. There were a couple of errors encountered. It fits all of the proposed forecast statistics. And once we've done that, everything looks okay. This looks a little bit less lumpy on the side now. We go into here, we can create a report, which is one of the things I always do. Press OK. It basically extracts everything you need from these reports. There we go, creating report. This is really interesting stuff. There we go, and then in the report there it stores all of the parameters, forecasts and assumptions that you've made. Let me just minimize that, and then I often extract the data as well. Pretty much do everything that it says. Then you've got it for posterity. Here you go. Here's all of the statistics and sensitivity work, and here are the trial values there, which I will now go away and analyze and show you those results later. One of the things, as I mentioned before, is that it does sensitivity analysis. I haven't quite got this right yet. Obviously the main sensitivity to hydrocarbon pore volume, this one here, is the choice of saturation height equation. So that has a 63%, as you might expect, I guess. What's controlling the saturation is in large part the saturation equation. But one of the things we're also interested in is what are the key sensitivities for the STOIIP overall, the GIIP overall. And so obviously the net to gross in layer 24, which is that large slab at the bottom or towards the bottom, all these things are dominated by the net to grosses and the GRVs of these lower slabs by the look of it. And then here we have the saturation height equation. Now I started off with one as a base case, and then some of them are a bit lower, but that's 2.5% contribution to the variance. So which from a previous work is plus or minus 3%, which is what I was kind of working out. So it seems to me, so if you include the unrealistic saturation height functions, i.e. the ones with just fixed saturations, then the variance is wider, so it's around about 3%, I'm sorry. But if I just took the realistic ones with rock quality terms in it, it seems to me, I think, unless I think about it a bit longer, my current conclusion is that the choice of saturation height function can make around about 2.5–3% difference to your saturation height function. And that's just the choice of function of the maths, you know, whether some functions are better than others or more theoretically valid with pore throat size and all that sort of stuff. At the end of the day, they're just mathematical fits, and they have a way of squiggling, and so the choice of function seems to be impacting things by plus or minus 3%. Okay, so back to the studio and hopefully wrap up with some more valid conclusions after I've thought about this for a little bit longer. Okie dokie, cheers then, thanks. Okay, so that was that Monte Carlo simulation. So the original simulation with all the functions, as you may recall, this is the whole total, all functions together give us a mean of 596 BCF plus or minus 50 BCF, if you like, and the impact of the saturation height functions was plus or minus 3% on hydrocarbon pore volume. So if we put an example of a single saturation height function from once I extracted the data, this is the lambda function overlaid with the total functions here. So this is the lambda distribution, and that was 586 BCF. And if we look at the average fixed saturation, that was the one with the 22% water saturation fixed. There, that's a bit higher. That's the 619 BCF. And then the one with the height only, remember, that was a little bit higher saturation again. So that was 634 BCF. But if we look at all the porosity-based ones, the porosity-based ones down to 599 BCF. These are the ones with rock quality terms in them. The Thomeer function, 590. The foil function, in this case, as I say, was pretty much the same, 588, with a range of that was quite similar to the Thomeer function in the blue there, the overlay. Then this is the Skelt-Harrison function. So you can see that all of the porosity-based functions are all falling in a similar sort of a distribution. And then the J function, again, is a little bit on the low side. So that Monte Carlo simulation that I ran with you, I showed you. Now that results in, let's just ignore these high ones, the height only and the fixed saturation. We just take those out. And then that tidies things up a bit. All the rock quality based functions are a little bit tighter, and as you'd expect, there's a little bit less variance. So let's round that up to 1.5 to 2% hydrocarbon pore volume difference in saturation height functions. So that looks quite good. And so we ran those Monte Carlo simulations, and this is again all of the saturation height functions were plus or minus 3.2%, and then those rock quality only ones were plus or minus 1.6%. So a much tighter range, as you might expect, by excluding those high ones. So one of the reasons that these talks tend to drag on a little bit is I kind of get distracted by various rabbit holes and disappear off down into various rabbit holes, and this one's no exception. So I think this is worth taking a look at. If we just disappear off down to down here, we can see that this reservoir, as I mentioned at the beginning, consists of two rock types. This is everything all together with the J function fit, and you can see I'm not catching this little rock type very well. This is quite a sharp transition zone, good quality rock, quite high gas saturations, increasing in this direction, down close to the contact, and my function is a bit lazy and it's not picking that up. So what's going on here? Well, if we just look at the Aeolian rock, the wind-blown rock, we can see that there you go. There's a better representation of that good quality rock. Now this is wind-blown. It's pretty well sorted. Dry canter, three-cornered rock, so it's quite good quality, and you've seen that everything together is a certain gas saturation, and then the Aeolian is the wind-blown stuff is better quality. If we just look at the fluvial data, you'll see that's poorer quality. It's got a longer transition zone. It's not quite as good as the Aeolian there. I toggle between the two. You'll see good rock, bad rock, good rock, bad rock. Actually, it's good rock and poorer rock is all. It's all still gas reservoir, still flows gas at quite high rates. It's all over 0.1 millidarcy permeability. But obviously, this is the log data, and you could say, well, maybe there's some artifact there. Let's check it up with some core data. We've got some core data. Some core capillary pressure data in the fluvial rock, and these are measurements made on saturation measurements made on single plugs. So this plug has a constant porosity, constant permeability, and it desaturates as we put gas in, if you like, in this way. And there's quite a good match to the log data, I think. So that gives us confidence that the log data is real, that this apparent longer transition zone is realistic. And if we look at the Aeolian stuff, indeed, that has a sharper transition zone, better quality, more gas in it for the given capillary pressure. And in fact, actually, it's probably over cooling, or it's got more gas in it than the log data would suggest. So there's something going on there, but you can see it's a much sharper transition zone. So if I toggle between the two, there's quite a difference in saturation between the two rock types. So therefore, if my overall function, this one here, is kind of an average of those two populations, I would hope that by modeling this separately with a sharp transition zone for this data and a poorer transition zone for this data, I might get a better match to the data overall, because on average, this is kind of like 15 PU rock. But if I had two different functions, one for the good rock, one for the bad rock, I might expect to get a better match to my log saturation and discretely describe the rock a little bit better. So that's what we're going to do. I'm going to come up with two functions, one with the saturation height function for the fluvial stuff, and one for the Aeolian stuff, and see what we get up with. So if I apply the fluvial rock type first, you can see I've got a bigger spread of data, which I might expect. The transition zone is more dominant, so perhaps there's more uncertainty with the fitting there, and I've got a spread of all the different functions in the fluvial stuff of 6 or nearly 7% by hydrocarbon pore volume. So that's kind of what I expect, a bit more smeared out in the fluvial stuff, and the Aeolian stuff is a bit tighter distribution, plus or minus 4 PU. So what's going on here actually then? Because I would have thought that everything together would have been more smeared out, but that's only plus or minus 2%. And then the Fluvial is plus or minus 7%. And then the Aeolian is plus or minus 4%. It's kind of not what I expected. The difference between the Aeolian and the Fluvial is what I expected. I expect the Aeolian stuff to be tighter, sharper transition zone, less spread. And the Fluvial, okay, I expect that to be the 7%. But I expected them both to be less than this 1% rock. So, what's going on then? So let's have a look at the individual saturation height function distribution. So here's everything together, which is my first Monte Carlo simulation run with the porosity, the selected rock quality functions with a spread of plus or minus 2% of hydrocarbon pore volume. Here you can see nicely well behaved, and here are all the individual functions broken out. So here's the porosity only one. Here's the Lambda function, the Thomeer function, Cuddy's foil function, Skelt-Harrison, Jenner, and the J function down here. So this is all of them together. This is the range, STOIIP range or GIIP range that they gave. So if I do have a look at the Fluvial functions, so I'm just going to run the Fluvial functions now. There's a much wider spread of functions, which I kind of wasn't expecting. I was expecting, as I say, I was expecting the Fluvial functions to have a bit more of a spread because it's a lazier function, more transition zones dominate, and perhaps the shapes of each of these functions differ in how they handle the saturation height functions. As I say, putting aside the correct physics about which functions handle things appropriately, they're all still mathematically derived shapes, if you like, and they cope with the transition zone. They fit to the transition zone in a bit of a different way. So I was expecting a larger spread with the Fluvial data, but I wasn't expecting it to be larger than the all functions together, which I assume would have been smeared. But anyway, so here is all of the saturation height functions in black again with all the Fluvial functions, and here are all the individual ones. You can see that the highest one here is the Buckles function, which is the porosity only one. Then we've got the Skelt-Harrison one, then the foil function. These are all quite high. They retain quite high gas in places. Again, the J function comes down as the lowest one, 501 BCF. But there's a spread. Now, if we look at this exact same thing to the Aeolian, and I keep these dots the same, so we've just moved. Where does the Aeolian move to? I expect them all to increase, and the majority of them do. This green shaded in one is the Lambda function, one of my favorites that I'm using as a kind of a reference, and you see that Fluvial to Aeolian, they generally all increase, but not by the same amount. They all increase by a different amount, and in fact, if you get your eye in here, you can see that the red one, the Buckles function, actually decreases. The foil function increases as well, the orange one, but the red one and the magenta one, which is the Skelt one, I guess the Skelt one has the Skelt-Harrison one has the same Buckles relationship in it. It has that A function in it. So we go from there to there. Let me just move those over here. So I'll just move those arrows over here, and you can see that the Lambda function has the most difference in it. It represents, remember the cap curve data had quite a difference in saturation in them. So there was quite a marked difference, and that's kind of reflected like, oh, actually, look, I missed this one. Sorry, the J function has the largest difference in them. Overall, saturation hydrocarbon in place increases by some amount between Aeolian from Fluvial to Aeolian. If I put those back there, that's So yeah, not what I was expecting, basically. So there's a tighter range in the Aeolian stuff. It's if I toggle between the two, you can look at how each function is responding. Here you can see I've still got some stuff here in, although this is the fluvial data in this rock. I mean, I'd have to go back and maybe check the classification in the rocks. But anyway, without getting too much further or bogged down into another rabbit hole, you can see that the saturation does change quite dramatically between the two. But the larger spread I hadn't expected. I would have thought that all of these ones together, being an average of the both populations, would give me a larger spread. But for some reason it's not. I guess I'll have a cup of coffee and sit down and think about exactly what's going on. But I think you can see, though, that different functions behave differently. And so what is going on? Well, maybe it's because this data here is not just controlled by porosity. So here's the porosity for the fluvial data. So that's 821 points. That's 400 feet of fluvial data in here. It's a fairly normal distribution, P90 to P10, average porosity 14.4 PU, and then the Aeolian, yes, the average porosity is higher, goes up to 15.8, so it's a PU higher on average, and the P10 seems to move a little bit. But actually, the overall porosity population is not that different between the Aeolian and the fluvial. If you look, the P90 stays the same. So that's interesting. This may be a case where we do need to go to that J function. If you remember, the J function gives the largest difference between the two, and that's probably the effect of permeability, because the porosities are pretty similar populations, and indeed that's potentially why the porosity-based function on its own is actually reducing, because you've got the effect of the lower porosity in those larger GRV slabs. Anyway, I'm starting to ramble a little bit now and getting lost in even more in the weeds than I normally do. Let's finish up with some conclusions. What have I learnt, or hopefully what have you picked up from this saturation height shootout, the conclusions? Well, first of all, I hope I've shown it's worth investigating more than one saturation height function. See how it impacts your reservoir and your particular reservoir configuration. Oftentimes, I'm just presenting one saturation height function to management and the reservoir and the modeling team, but it's worthwhile if you just to check out a few and recognize whether you have a significant transition zone in your reservoir, because as I hope I've shown that with those functions, the way that those mathematical forms bend around to match the data, each function can handle it a little bit differently, and so therefore you might have slightly more error or uncertainty in how your function, your particular favored function, handles the transition zone. So obviously related to that is you should understand the GRV distribution within your field. Where is the rock in your reservoir? If you've got a large transition zone and a large slabs of rock, large GRV down at those low elevations in your reservoir, then obviously that's going to have a bigger impact again, and again more uncertainty. Obviously, I think, as I've said, do you really need to use permeability to differentiate rock types? And in this particular example, I'm coming to the conclusion that I probably do need to go to a permeability-based function. As you saw there was quite a bit of spread in the saturation, but not much spread in the permeability. In the porosity population, they were quite similar between the two rock types. So that kind of infers to me that the permeabilities are different. And I think, if I can remember, the average permeability of the Aeolian stuff was around about 150 millidarcies, and the average permeability of the fluvial stuff was down at around about 50 millidarcies. So on average, that's quite a contrast. Individual plugs and permeability and intervals are up to about 4 darcies, I think, in the Aeolian stuff, and up to about 1 darcy in the Fluvial stuff. So how that's handled, given that the porosities are similar, that's probably why I need to resort to the GRV. Sorry, the permeability related functions, and you saw there that J function had the biggest contrast. But as I say, my normal modus operandi is I prefer to use porosity based functions in the first instance because they're a bit simpler. There's less uncertainty introduced by having to map or predict permeability away from the wells and in distribution in your model. And also, if you've got a permeability related saturation height function, when the reservoir engineer wants to multiply things by 7, the permeability by 7, or divide it by 2 to match his flow performance, then that can obviously have an impact on your original hydrocarbon in place, and that adds extra complication. You probably need to recalibrate your saturation height function at that point to the appropriate revised permeability. Anyway, typically log analysis error, the rules of thumb that I carry around in my head are normally 1 or 2 PU in porosity error, 6 to 10 to 11 saturation units in log saturation. At higher hydrocarbon saturations, the error is less. So at 96% oil saturation, the error in water saturation is lower. But at lower oil saturations, around about 45%, oil saturation, say, the saturation uncertainty would be plus or minus 7 to 12 saturation units, for example. Typically, those are the sorts of numbers that I carry around in my head, and that typically results, by the time you multiply up those porosities and water saturation uncertainties together, that typically results in a 5 or 10, 15% uncertainty in hydrocarbon volume due to the log analysis. When you get to multi-wells, and if you watch my trendy Petrophysics and my sums and averages presentations, you'll see that the confidence in the mean may reduce the error or the uncertainty a little bit as you sample more and more of the geology and sample random wells as well. You may have one well, as I say, that is calibrated with a dodgy density log in one way, and then the next day or the next well might have a high porosity and a low porosity, and it might cancel out overall. So the law of large numbers might come to your defense. But if you've got the saturation exponents wrong or the water salinity wrong, then it'll always be wrong. So those systematic errors will remain. But that's typically the error analysis I've seen to do with the log analysis. But what I hope this work shows is that the choice of saturation height function itself seems to make, between 3 and 7% hydrocarbon pore volume difference, and that's just in the maths of the saturation height function, the shape of the saturation height function, and how it characterizes your reservoir. So hopefully you found that interesting. There was a paper in 2007, I think. I may put the link in the description below, of different saturation height functions. Heriot Watt University put it together. They had a digital paper shootout. This is my 2020s digital YouTube version of that, and I hope you found it interesting. There aren't that many places that do the saturation height comparisons. I don't think you tend to, in the real world, you tend to just pick your favorite function and go with it, and that's what you present to management and the team. But I think hopefully I've shown that there's worthwhile exploring a few just to see what they look like with your data. Okay, thanks a lot for your attention. I'm sorry again. Once again, I've drifted on. I mean, I guess those who are still here are probably serious about their petrophysics, a bit more serious about the petrophysics. So hopefully that's been useful for you. As I say, I'll put a link to the error analysis spreadsheet, which is part of the residual oil presentation I made. It discusses some of the uncertainties and error analysis and log analysis there, and then you can refer to the sums and averages ones about the confidence in the mean approach and the reduction in uncertainties when you have the law of large numbers on your side. Okay, thanks a lot for your attention. I hope you enjoyed it, and I hope to see you back on the channel very soon. Thank you.